So let's understand this, how to define an Hamiltonian. So the original equation are mq dot dot plus kq equal f. Okay, this is our original system. As a physical quantity, we can introduce the momentum p, which is given by the mass times q dot. Okay, so if I do that, I can rewrite this the dynamical equation as mq dot dot is equal to mq dot the t dt, but this is equal to the p dt, right? So I can rewrite mq dot dot plus kq equal f as the p dt equal minus kq plus f. But then I also have this equation, which I can couple it here. I can couple it to this other equation and write the q dt equal p divided by m. Well, this is a simple rewriting of our equations, and this is basically, these are the Hamiltonian equations in terms of the conjugate variables p, q. You see, we will understand now what is so special about these two variables. These are not only we have to understand what does it mean to be conjugate, and also p and q are also canonical. So we have two concepts: conjugate variables and canonical variables, which means the same things. So until now we simply did a rewriting of the equations, and which we went from a second order ODE to a first order system of ODEs. So that's what we have done it from a mathematical perspective. Let's understand a little bit better this formulation. Okay, so we saw that we can rewrite these equations by introducing the momentum variable mq dot and then we have also the variable q, momentum and displacements, and we can rewrite our system as the p dt equal minus kq plus f, and the q dt equal p divided by m. But let's reason on let's spend more time on this system. In particular, I know that the kinetic energy is equal to 1/2 mq dot square, which I can rewrite it as 1/2 mq dot square divided by m, so 1/2 p square divided by 2m, or let's say p square divided by 2m, and the potential energy, is simply a function of q, and is equal to 1/2 k q square minus f q. And then, based on this, I can define the total energy, which I'm going to call it h, which will depend upon p and q, as k plus p, which is equal to p square divided by 2m plus 1/2 k q square minus f q. This is my total energy. But now it is easy to see that this term here, minus qh plus f, is simply minus the partial of the total energy h with respect to q. It's right, because I'm gonna get minus kq plus f. And then it's also pretty straightforward to realize that p over m is plus the partial of h with respect to p. Okay? So this is pretty straightforward, and actually now we get this alternative, more general formulation, the pdt equal minus partial of h with respect to q, and the q dt equal plus h with respect to p. So we call h the Hamiltonian of our system, which in this case is the total energy of the system, okay? So not necessarily the Hamiltonian is always the total energy of the system, but for the system, for a mass spring system, the Hamiltonian is the total energy. So this is the Hamiltonian formulation of our dynamical equations. And now we start to see some structures here, actually what is called a symplectic structure. Which now we're going to symplectic. Let's try to understand, all these fancy words, what they mean. So, but until now, in general, no, we were able to define an Hamiltonian H, we depend upon P and Q, for the mass spring system. H is equal to the total energy, equal to K plus P, okay? And we were able to rewrite the equations as this coupled system of ODEs, and what is so special about these systems? Well, first of all, no, we need to, if this is a good Hamiltonian system, we need to derive what are they called the Poisson brackets. A good Hamiltonian system is going to have good Poisson brackets. So let's try to understand what is this concept of brackets. And to do that, let's consider a generic observable, which is basically any function f which depend upon p, q, and t. For example, I can have f equal to k plus p equal to h, or I can have f equal p, or I can have f equal q. These are examples of observables, okay? We would like to understand what is the rate of change of f under the dynamics of this system, okay? So we would like to compute, to evaluate the total derivative of f with respect to time. But this is equal to what? This is equal to the partial derivative of f with respect to time. In general, this function f can also have an external time dependence, which doesn't come from the intrinsic time dependence induced by p and q. Okay, so this is simple partial of f with respect to t. But then we have to consider the time dependence that comes from the fact that f can depend in general by p and q. So I have a partial of f. I'm gonna do the partial of f with respect to q times the q dt plus the f with respect to p times the p dt. But now I can exploit the properties of my system which satisfy these equations, and so this is this, and this is gonna be this. So I can rewrite this system, this expression as the partial of f with respect to t plus df dq times partial of h with respect to p plus partial of f with respect to p times minus partial of h with respect to q. Now you see that a structure appears here, okay? So we get these nice results. We can write the time derivative of the total derivative for any observable f in terms of the Hamiltonian, the derivatives of this Hamiltonian, okay? Actually, there is an extra structure here. Let's understand what does it mean. So I can rewrite this expression as the total derivative of f with respect to t equal partial of f with respect to t plus dfq times dhp minus dfp times dhq. And now we can rewrite these terms as as f comma h. Okay, so we're gonna have the new definition of df dt equal the partial of f with respect to time plus the Poisson bracket between f and the Hamiltonian. This is the Poisson bracket. So, and this is the definition of we derive this devolution equation for any observable f, which now is written in terms of this Poisson brackets plus a time derivative, a partial derivative in time, which depend upon the extrinsic dependence of f on time, but the intrinsic dependence on time, which comes through the dynamics, is given in terms of these Poisson brackets. And as I show you in general, we have that the Poisson bracket of two functions a and b is equal to the partial of a with respect to q times the partial of b with respect to p minus the partial of a with respect to p times the partial of b with respect to q. And what are the properties of this Poisson bracket? Properties. Well, first of all, it is antisymmetric. So a comma b is going to be equal to minus b comma a. Then this implies that a comma a is always equal to 0. And then one important property is the Jacobi identity, which means that if I have a bracket with bc plus, now I shift cyclically on these three terms on this on the right hand side to the right hand side, and so I'm gonna get c comma a b plus shifted again b comma ca has to be equal to 0. Okay, and this is the most important property of a bracket. Okay, so it should, in order to have a good bracket, the Jacobi identity has to be satisfied. Now it's very easy to check that it's just some cumbersome algebra and calculus, but you can easily show that these properties are satisfied. Okay, once you have a good bracket, now you have total control on the problem, and you can derive any dynamics. Okay, even from this relation and the knowledge of the Poisson bracket and the Hamiltonian, I can derive any. I can even derive the dynamics of P and Q of my original variables. So that's all this math to basically rewrite our system. So given H with Hamiltonian and good Poisson brackets, in our case, AB, we satisfy the Jacobi identity. That is the most important one. Then the evolution of any observable f, which depend upon p, q, and also can have an extrinsic dependence on time. Extrinsic dependence on time. And here I have intrinsic dependence on time via dynamics of PQ. So the evolution of any observable is given by total time derivative df dt equal partial of f with respect to t plus f bracket with the Hamiltonian, and that is the main results. Once you do that, you will have an Hamiltonian formulation of your equations, and from this evolution of a generic observable, we can even derive the original equations, the original Hamiltonian equation for P and Q. Indeed, to do that, no, you can set F equal P, and at this point, you know, this relation is gonna give me what? It's gonna give me simply the P dt equal this partial derivative, there is nothing. Then I have what? P bracket with the Hamiltonian. Okay, but this is equal to what? By definition, this is equal to the P, the Q times the H dP minus plus the P times dH dQ. But this is equal to 0, this is equal to 1, so this is equal to minus dH dQ. So we have the P dt equal minus dH dQ. So for this observable, we derive the P dt equal minus dH dQ. And then we can do the same for Q. Let me redo it here. So we have the F dt equal partial of F with respect to t plus F bracket with H. The general definition of bracket AB, of good brackets, is dH dP dB, dQ dP minus dA dQ minus, oh my gosh, I always get confused here. Let me see what I wrote before. Minus P times Q. Okay? So, if I do F equal Q, then I have what? I have that dQ dt is equal to 0. Then I have what? I have Q comma H. Then if I do F equal P, I will have the P dt equal P comma H. But this is equal to what? This is equal to the Q times dH the P minus the Q the P times dH dQ. And this is equal to 1 and this is equal to 0. So I get dH dP. Instead here I have the P, the Q times dH P minus the P times dH dQ. But now this is 0 and this is 1. So this is equal to minus dH dQ. So we have that this is equal to this. The P dt is equal to minus dH dQ. And then we have that this is equal to this. The Q dt equal to plus dH dP. And we recovered the original Hamiltonian equations. Now I can also consider as an observable, let me do it here, if F is equal to H, dF dt is equal to the f partial of f with respect to t plus bracket of h with h itself. But this is basically disappearing, so we have the bracket of h comma h, and this is equal to 0. So h is conserved. And that is the main property of an Hamiltonian system. If you get an Hamiltonian system, you have an Hamiltonian, and this Hamiltonian will be automatically conserved by the flow. These dynamical equations now can be interpreted as a flow in the time domain, in the domain